thankfully he kind of leaves it alone. But like if you look at my leaves, my poor plant, there's like scars from like him biting it and stuff.
You gotta get him a little grass, right? A little cat grass.
Yeah, no, he just gets into everything. He gets on my shelf. I think once he like calms down, it'll be good. If you adopt another cat, I doubt it.
All right. Well, I'm not going to wait for the other half of the class to show up, and so I'm gonna get started here. I need to double check the time. It's like, oh, am I really sure that I'm not 15 minutes early? Because where's the other half of the class, right? Well, it's all getting recorded as long as they show up before I take roll. Everything should still be good. All right, so we are in week 3. We have completed 2 weeks already. So congratulations, because we're back on campus and, everything seems to be doing okay. Um, so right now, today is going to be a good test of whether you guys have been absorbing the material and whether you have been taking effective notes during class, because today's lab is going to be a little bit more involved than the usual. But I will go through a lot of the terms, definitions, and whatnot that you need to know in today's lab. So, if you take notes and pay attention, I think you should be fine. But I'm just reporting what I saw yesterday from the Tuesday, Thursday class. All right. So I got a few technology. Oh, by the way, I put in an announcement for Z-Day. So I just want to talk about it a little bit. I am not a spokesman for IBM. They did not pay me at all, like not even in peanuts or food or anything like that. But I think it is good to talk about it from your perspective, because there's a link here. You guys can click the link. So I want to mention this because IBM mainframes are usually seen as really archaic, antique, and nobody wants to touch it. Well, that is partially true, okay? Because the current IBM mainframe computers are backward compatible to everything back in the 60s. So if you have a program originally written in the 60s, not modified in any way to conform to the new standard, it will still be able to run on a modern day IBM mainframe computer, which is nice in a way, but it's also problematic in a way because it doesn't help motivate companies to move on to newer programming languages, databases, and so on. So of all those organizations who refuse to move on are many of our California state departments, like the DMV, the Board of Equalization, the BOE, the Franchise Tax Board. It also includes a lot of private and kind of prominent organizations like American Express, Walmart, Wells Fargo Bank. So they are all still running IBM mainframe computers. The biggest problem they have is they got people retiring and also passing away. I mean, those programmers from the 60s, some of those are dead now. I mean, they're really old. And yet we don't have enough people to move back into that industry, so they have a shortage. So if you guys are looking for another opportunity of employment, after you graduate from, a 4-year university, this is one possibility. Okay, it may not fit what you want to do. This may not be you at all. But for those of you who want to explore, just possibilities, this is one more thing to explore. All right, so that's all I'm going to say. There are some events, included in this link here. They are next Wednesday. So next Wednesday, the 14th, is the first day of the conference. They also have a contest. So if you guys like to win stuff, there's a contest. It's not hard stuff. If you're in this class already, I think you guys can learn everything that you need to learn to win. There's also a IBM hosted, how should I put it? It's kind of like a learning module thing, but you can earn badges. So if you earn those badges, potentially in the future, if you want to work for an organization using IBM mainframe computers, it might possibly count for something. Okay, so just opportunities right there. And with that said, I'm going to move on to the addition that I mentioned earlier. Let me see, Joplin, that's it. So what we'll do today first is to kind of perform a binary addition using the structure that we have talked about so far. So I'm just going to use this to help you to kind of remember or to remind you of the terms, definitions, and whatnot that we have talked about so far. And to do that, I am going to use my somewhat high-tech approach, which is a tablet with my stylus, and I want you to be able to see it. So let me pop that window open here. All right. So I think okay, let me double check the number because I forgot about the numbers that I'm supposed to be adding. It's 110, which is 6, and 011, which is a 3. Okay, so we got oops, wrong color. So we got 110 plus 011, and this is all in base 2. All right, so what do we do? But remember, this is in base 2, okay? So I'm going to number or label the rows. This is Y, okay, top one is X, and then Y, and then we have Q, we got K, and then we have S for the sum. So I'm going to draw another line over here, and then we have another addition. All right. So the one thing that we also know, would be K0. K0 can be assumed to be 0. In most cases, not all, but in this case, we can assume that to be a 0. So can someone remind me how we can compute the Q? What is the definition of Q of I in general? So Q of I in general is, which function do we use? Okay, we got two functions that we have talked about. One is R, and the other one is C. So which one do we use to compute the Q of I? R, okay, very good. So Q of I is R of xi, yi, and then S of I is R of qi, ki. All right. So those are definitions based on the structure of multi-digit addition. It is not specific to base 2 or base 10. It doesn't matter which base we're dealing with because of the way we define the R function. So the R function is also known as the single-digit sum function. So in base 10, 6 and 7, would have a result of 3. So 3 is the single-digit sum between 6 and 7 as base 10 digits. That is based on how we define the R function, which is also in the notes. So I'm hoping that you guys actually found some time to read the notes because that's where everything is coming from. So I'm going to go back to the notes, which is, it's titled binary addition, but it also has a definition of the R function, which is the sum of the two single digits. And then in this case, it's modded by 10 because it is specifically for base 10. So we also talked about how we can cater this to work with base 2, and what was the idea to change this to work with base 2?
You change the 10 to a 2.
You change the 10 to a 2. Okay, it's as simple as that, okay? So that's one. And then we'll go back to the example. So now so we can now work out the Q's. So 0 plus 1 is 1. 1 mod 2 is 1. 1 plus 1 is 2. 2 mod 2 is a 0. 1 plus 0 is a 1. 1 mod 2 is a 1. So that's how I can compute all the Q bits, okay? And then what about the carry bits? The carry bits are defined to be the single digit sum. If it is greater than or equal to the base, then it is a 1, otherwise it is a 0. That's how C is defined. And if you want to go back to the notes, this is also showing you how C is defined. We take the two single digits out of base 10 in this case, we add them up. If the sum of the two digits is greater than or equal to 10, then we return the value of 1. Otherwise, it returns a value of 0. So it determines whether we have a carry or not. So how did we change this C function to work with base 2?
Change the 10 to a 2.
Change the 10 to a 2. It sounds like I've heard that before, deja vu, right? Because it really is just that simple. Okay, you change the 10 to a 2. All right, but the C function alone is not enough to solve the problem because we have two ways to have a carry. So between the x and the y, there's a way it can potentially generate a carry of 1. Between the q and the k, we can also potentially have a carry of 1. So in this case, if I'm looking at k1, which is here, what should it be? Now remember, this is base 2 addition. So now we look at, okay, let me see if I can move my mouse pointer here so I can actually point out. So if we add 0 and 1, does it generate a carry of 1? Nope. What about adding 1 and a 0? Does that generate a carry of 1? No. Okay, so we got no, no, but how do we combine those two no's or false into the value of this particular carry bit?
Carry is R of Q and K.
It is a OR. Very good. Okay, so it's an OR, which means false and false. False or false is false, which is represented as a 0 here. So the general equation for the k bits is k of I plus 1 is defined to be the carry of xi plus yi, or, so I'm going to use or here, the carry of qi added to ki. Does that look familiar to you? I sure hope so, because that's in the module, and that's also what we talked about last week. Are we okay so far? Good. All right. Excellent. So now we can work out the other carry bits. What about this carry bit right here? What is it supposed to be? Let me move my mouse pointer so I can actually get this recorded. What about this position here? It's a K2 in this case. Oh, okay, I can probably disable Discord for now. So I'm gonna get rid of Discord so it doesn't distract us. There we go. Quit. There we go. All right, so what about this position here? What would be I in this case? Because we're trying to figure out K of 2. So if K of 2 is what we need to figure out, what would be the I over here?
1.
It'll be 1. So we'll be looking at C of x1, y1, and what would that be?
X1, Y1, 1, 0, 1, 1.
So we have 1, 1 as x1, y1. So when you compute the carry of 1, 1, it is a 1 already. Since this is a logical OR, if at least one side is true, the whole thing is going to be true. So now we know we're going to end up with a 1 over here. Is that okay? So now we want to look at K3, which is here. This is K3. So what about K3? What is the value of K3? It's going to be the C of x2, y2, right? C of x2, y2 is not going to be a problem because x2 is a 1, y2 is a 0. So the carry between those two would be a 0. Because 1 plus 0 is not greater than or equal to 2. 2 is the base in this case. But what about Q2, K2? Q2 is a 1, K2 is also a 1. 1 plus 1 is 2. 2 is greater than or equal to 2. So that means this component here is going to be a 1 when I equals to 2. So that means we end up with a 1 here as well. So we end up with a 1 here. So I'm going to use the red color here to kind of indicate to why we end up with a 1. So this is the first one, and this is the second one. Do we have any questions about how we figure out K1, K2, and also K3 in this case? Questions? All right. The carry bits are fun, but that's not our objective, okay? Because what we really want to do is to figure out the sum bits. So the sum bits are the R of Q and the K. So we have 1 or 1, 0. The R of between those two is a 1. The R of 0, 0 is a 0. The R of 1, 1 is a 0 as well. And that would be the answer. Because in multi-digit addition in this class, we want the sum to have the same number of bits as x and y. So this is a 3-bit adder, so we want the sum to stay with only 3 bits and not 4. But is it still representing the correct sum? Well, let's figure out. 110 is 4 plus 2 plus 0, which is a 6 in terms of the value being represented. 011 is 2 plus 1, which is a 3. So we're looking at 6 plus 3. So is 6 plus 3 1 with a carry of what? What is that carry representing?
8.
It's representing an 8 because which column is it on? It's in column 3. So it's digit 3, which means it is representing a 8. So we have 8 plus 1, which is a 9. Sounds good to me. 6 plus 3 is 9, right? Means so everything still works out. It is just the value being represented by the sum is no longer just contained in the sum itself, but also we have to look at K3 in this case as part of the result. Are we doing okay so far? Okay. So the other way to do this computation is to use the bitwise operator or the logical operators. Because one thing that is fun about base 2 is the R function can now be implemented using logical operations. So can the carry function. Do you guys remember that? The carry function is simply a logical AND. The R function is technically an exclusive OR, but it can also be expressed using negation, conjunction, and disjunction. So we talked about that a little bit. So in base 2, okay, only specific to base 2, R of AB can be expressed as A exclusive OR B. That is the symbol for exclusive OR. But if you do not want exclusive OR, you can also re-express it as not A and B, or A and not B. I'm using the shorthand that I have introduced already. The shorthand as a notation is also in the module. Okay, so that's why reading the module is so important because none of this is new. Okay, maybe the way I present it is a little bit new, a little different from the module, the written module, but there's nothing new here. The carry of A and B is simply A, B, or A and B. It looks like A times B, but I'm using the multiplication notation to mean conjunction when we're dealing with Boolean values. So I have to be more careful here because I have to say in base 2.
Right, so like A times B is just the way you say A and B?
That is correct. Yep. Mm-hmm. Just because I'm too lazy to use the wedge symbol or...
So that A, not B, that's A and not B.
That is correct. Yep. Mm-hmm. All right. Well, technically, the parentheses are also not needed. In other words, these pairs of parentheses are not needed because of the priority of operators. Because in normal algebra, we prioritize multiplication and then we perform addition. So I'm keeping those your priority ranking of the operators when we translate into Boolean algebra. All right, so this is a recap. Yes, go ahead.
Does the plus sign mean or?
Yep, it is. So all of that is part of the module, okay? So it's important for you guys to pick up the notation, the symbol definitions, and all of that by reading the module. But I'm kind of making it very explicit right now because this is the sort of thing that you need to know in order to do the lab today. Well, a portion of the lab relies on this, and then a portion of the lab relies on what I'm going to talk about. Okay? So are we doing okay so far with this? Last week on Wednesday, I also gave you the carry ripple adder. Do you guys still remember the carry ripple adder that I worked out during class? Okay? No? It consists of, the first thing I did was to construct an exclusive OR, right? And then I constructed the half adder, and then I constructed the full adder. Did I not do that with this class?
Yes,
Okay,
yes.
I did. Okay, very good. Because I was just about to go to YouTube and double check. Because my own memory is a little fuzzy, because I'm teaching two sections of the same class. Sometimes it's harder to remember. Did I talk about this in this class? And turns out other instructors have the same struggle if they're teaching multiple sections of the same class. So anyway, so what is the one problem with a carry ripple adder? I kind of mentioned that at the end of the section.
Takes time.
It takes time. And how bad is it? So if I were to compare a 4-bit adder as opposed to a 64-bit adder, would the amount of time change because one is a wider adder and the other one is a narrower adder?
Yes, more carries right there.
Hmm?
More carries to talk about?
Yep.
So that's
And,
why-
and how would that impact the time? Comparing a 4-bit adder versus a 64-bit adder. Go ahead.
The ripple adder is linear time.
It's linear to the width of the adder. So that means a 4-bit adder is going to take only 1/16 of the time of a 64-bit adder. Because you have to wait for the carry. K1 depends on K0, K2 depends on K1, K3 depends on K2, and so on. So Ki plus 1 depends on K of I. So now you have this linear dependency. Even though all the gates are operating all the time, whether they give you the correct result is the problem, because it takes time in order for the right value for the carries to propagate through from the low order bits to the high order bits. So that's one problem, okay? It's not a problem if there's no faster way to do it. In other words, if Intel and AMD, they both agree, it kind of sucks that we have carry ripple adders, but there's no better way to do it, so there's no problem, okay? Because it's going to be about the same between the AMD processors and the Intel processors. But if one company finds a better way to do it and make it constant time and not dependent on the width of the adder, the other company now has a problem, don't you think? Because now AMD can say, our processors can do adding a whole lot faster because we have this special technique. And then Intel processors now cannot sell because they cannot do it as quickly. So we actually have a faster way to perform binary addition. It's still based on what we learned up to here, but it has a little spin to it. So that's going to be the focus of today's lecture. You might want to write notes, even though I am recording. I'm double checking to make sure that I'm not. Yep, I am still recording. You guys cannot see it, but I double checked and verified. So we're still recording, but you might want to write down notes because your lab today relies on what I'm about to talk about. And there are some definitions, that are definitely going to be important when you are doing your lab. So where we are now in the module is in section 6. So this is section 6. Section 6 talks about why carry ripple adder is, even though it's simplistic and it's very scalable, because you just stamp out those full adders and you keep connecting things and you can make it wider and wider. It has this problem of it's not very fast, okay? And there is a faster way to get things done. So what we want to do is to say, okay, what can we do about making things go faster? So the first thing that I do is here. I made some changes. So if you had downloaded this HTML, you might want to download it again because I made some changes. There are something added to this. So the first thing I did is this entire derivation. I will briefly go through each step. Okay, that is not the main point of the derivation, but some parts of this I think really should not be a big surprise. The first one is how the structure of adding works. Okay, in other words, the first part here, the first line of definition, that works across all bases. It's not even specific to base 2. This works regardless of which base we're dealing with. This is just how we perform multi-digit addition. So base 10 has the same equation. But going from the first line to the second line, it relies on how we perform the C function in base 2 only. So now we are making it very specific to just base 2. So in base 2, we use the conjunction, to implement the carry function. It's a simple conjunction. So, and then from the second line to the third line, it depends on how Q is defined. And once again, Qi is R of xi, yi is across all the bases. It is not specific to base 2. But from line 3 to line 4, that is once again specific to base 2 because we are looking at the R function as the exclusive OR between the xi and the yi, which can also be expressed using this formula here. And then from the 4th line to the 5th line, it is distribution. It works just like distribution in normal algebra, where we distribute k of I to the 2 individual terms in the summation. And then from distribution, we have identity. This looks the same as identity in multiplication in normal algebra, because anything times 1 is that anything. So we're not actually changing anything. The next derivation is specific to Boolean algebra, which is true or whatever is true. Now, does that make sense to you? If we have a disjunction, or if we know that one side is true already, then it doesn't matter what the other side is, it's going to be true. Okay? So if you are not convinced, I would recommend you to use a truth table so that you can convince yourself that it makes sense. Okay, so that truth table is going to have one single independent variable. You have one, or true as one column. Okay, that's a simple column. And then the other column is going to be true or whatever that independent variable is. You just have to double check to make sure that the true column has the same value as the true or whatever column for every single row. Okay, so I'm going to leave that exercise to you. But this is something that you can only do in Boolean algebra. The plus is not really an addition, it is a OR. From this line to this line, I am relying on identity and distribution because this one is distributed to xi, yi, and then I simplify that because it doesn't really do anything. But this ki is distributed to xi, yi, even though it doesn't really change the overall expression. I want this term to be all by itself here. And then the next one is x plus x is x, which is not really saying the sum of x is the sum of x and x is x. It is saying the disjunction of x and x is x. Okay, x or x is x. So the way I do that is so that I can duplicate. So you can see how there was only one of these terms here. Now we got 2 of those. Okay, but it doesn't really change the expression of the disjunction because Can everybody say this just kind of intuitively understand that x or x is really just x without using a truth table? Okay, all right. So if you want to use a truth table to prove that to yourself, that is also recommended. The next line is I mistyped it. It really should not be commutative. It should be associative. Because I'm just basically saying, oh, let's group these two and group these two together into its own term before we OR that term with the rest. So the ability to restructure how we perform the disjunctions within a sequence of disjunctions is associative and it is not commutative. Commutative means we can change the ordering. Associative means we can change the structure of what do we evaluate first. And then the next one is factoring. We can recognize that xiki, xiki are both common to these two terms, but the yi is on one side and then the not yi is on the other side. It is factoring, which is reversed distribution. We're basically just saying, oh, okay, wait, instead of the addition or the OR of these two complex terms, we can now say, let's extract the common part xiki and then and the parts that are not terms. And then we do the same thing with these two. After factoring, we have x or not x being 1, being true. Does that make sense to you? Regardless of what x is, x or not x is true. Now, intuitively, it should make sense because if you look at x versus not x, one of them has to be true. And since we're looking at the OR between those two, that means if at least one of those two is true, the whole thing is true, which means, oh, okay, well, then it has to be true regardless of what x really is. Once again, you can use a truth table to prove that to yourself. So by doing that, now we can combine xi or not x, yi or not yi into true. We can also combine xi or not xi to be true again. And then we use identity because if you have a conjunction and one side of the conjunction is true, then you don't need the true in the conjunction. So we just simplify the one out. And then we do another factoring because out of xi ki, yi ki is common. So we extract the ki out, and then we perform factoring so the xi or yi becomes its own term in the conjunction. So some of these steps are pretty much the same steps that you can take in normal algebra, and some of these steps are specific to binary, or I should say Boolean algebra. All right, so don't you guys love algebra? I do. Okay, wait, hold on a second here. This is a computer science class. Why are we talking about algebra? I don't think we need to understand algebra in order to be a successful programmer or computer scientist. What do you guys think of that statement?
I think that's false. I just been recently doing a lot of like leak code problems to try to stay fresh and job ready. And a lot of it, like when I started programming, I thought it was just gonna be, the program, the language, but it's actually most of the work is like figuring out a system, figuring out the patterns, and it's a lot of just like, say you have a grid problem and you wanna like select the even numbers. How do you represent that in like mathematical speak? It's like a lot of math, to figure out the actual problem.
Yep, absolutely. I'm glad you brought up lead code, which is one way that you can prepare yourself for job interviews to get a job. So that's good. The other thing that's why algebra is actually important is there are many ways to express the same thing. So when you are reading somebody else's code, somebody else may decide, oh, I want to express this, using this expression here, when it can also be known as this expression, this expression, this expression, and this expression, and so on. So being able to recognize that these expressions are all equivalent is important because otherwise, we'll be looking at somebody else's code and have no idea what it is talking about. So algebra is important in computer science. So is math in general. Math in general is also important in computer science. All right, so somebody is going to look at this and look at the final result here and go like, Tech, but you didn't really quite solve the problem because I can see how k of I plus 1, which is up here, still depends on k of I. You have just changed the thing a little bit so we can now re-express how k of I plus 1 relate to k of I. Well, you are absolutely right. I have not solved the problem yet, okay? But I have changed the format so I can get a little bit closer. So this is also important. So you might want to note this in your notes because in your lab today, you will be required to understand this part. G of I is defined to be xi and yi. That's just how it's defined, okay? And then P of I is x of I or y of I. That's just how it's defined. So with those two terms defined as they are here, G of I and P of I can now rewrite K of I in a slightly different way. Not too much different compared to before, just a little bit. So let me see if I can scroll the screen to exactly where I need it to be. So now I can look at this K of I being xi and yi, or xi or yi, the whole thing, and ki. So instead of doing that, I can now simplify, because I have now defined what is gi and pi. I can now simplify that to be k of I plus 1 equals to g of I, or p of I and k of I. Are we still doing okay so far here? Because all I did here is to define g of I and p of I, and then instead of using the xi and yi, xi or yi, I can now refer to those two as g of I and p of I. Are we good so far? All right? And someone's going to complain and go like, but Tech, you're still not solving the problem because we still have a dependency of k of I plus 1 on k of I. You're right. Okay, so we are going to take this and see what we can do with this more general format or template of computing k of I plus 1 from k of I. So the first thing we do is to say, what if I is 0? Okay, if I is 0, then k of 1 is g of 0 or p of 0, k of 0. Or I should say g of 0 or p of 0 and k of 0. And it is represented down here. So let me just kind of go down a little bit here. So now we can resolve, if I equals to 0, then we end up with this equation here. Are we good so far? Because that's just plugging in I equals to 0 to k of I plus 1 equals to g of I or p of I and k of I. All right, hardly exciting, right? It's like, yeah, no big deal. So what we'll do next is to say, what about k of 2? Okay, because if we want to figure out k of 2 using the template that we have already up here, that means we have to substitute I equals to 1, right? So if I equals to 1, then we have k of 2 being the same as g of 1 or p of 1 and k of 1. You go like, oh, okay, Tack, you haven't solved the problem because I can see how k of 2 is depending on k of 1. But hold on a second here. I already know what k of 1 is, right? So I'm going to plug in what I know k of 1 is based on this equation here. I just plug it in, okay? So k of 1 is the same as g of 0 or p of 0 and k of 0. And once I plug it in, I will go ahead and do distribution. So now I have a final form of k of 2 being g of 1 or p of 1 and g of 0 or p of 1 and p of 0 and k of 0. That was supposed to be the magical moment. The non-Disney magical moment. Do you guys see why I call that the magical moment? What just happened?
K is gone.
No, K is still here.
Did everything to K0?
K, exactly. We boil everything down to K0. K of 1 is gone. K of 0 is one of the inputs. And the G's and the P's, they are all computed from the XY anyway, so they're easily computed. So in this final form, we have just broken the linear dependency. K of 2 does not depend on K of 1 anymore. K of 1, guess what? You get yourself your own equation to figure out yourself. But K of 2 says, I don't need to know what is K of 1. Just tell me what is K of 0, and I can figure out my own value. We have broken the linear dependency. Are we good so far? Maybe? Okay. What about K of 3? So if we plug in I equals to 2 into this particular template here, the first thing we got is K of 3 is G of 2 or P of 2 and K of 2. You go like, oh, here we go, another linear dependency. But guess what? At this point, we already know what K of 2 is, so we plug it in. So we look at K of 2 being this expression here. Yes, it is a little bit complex, but nonetheless, it does not depend on K of 1. So we plug that in, so now we can know that K of 3 is G of 2 or P of 2 and, in parentheses, G of 1 or P of 1 and G of 0, or P of 1 and P of 0 and K of 0. And then we use distribution again, so we now end up with G of 2 or P of 2 and G of 1 or P. Okay, I'm not going to use the and the or anymore. I'm just going to say P2 P1 G0 or P2 P1 P0 K0. In other words, I can now express K of 3 with just K0 and all the P and the G terms without the linear dependency anymore. Are we doing okay so far? So I didn't show here, but if I want to figure out what is K of 4, what would be the approach to solve for K of 4? Can you guys tell me, just based on what you have seen here, what would be the technique to solve for K of 4?
Would it be G of 3 plus P of 3, K of 3?
But what would be the approach? The approach is we first plug in I equals to 3 into the template that we have up here, right? We just plug in what if I equals to 3, because that would give us the template to solve for K of 4. But then we'll end up with something that looks like this. K of 4 is going to be G of 3 or P of 3 and K of 3. Then we go like, oh, but what can we do about this K of 3? We already know what K of 3 can be expressed as. It's just a long, kind of complex expression, but nonetheless, it has no dependency on K of 2 anymore. So we plug this in to K of 3, and then we just do the distribution. Then we end up with an even longer expression like this to solve for K of 4. And then we do the same thing with K of 5, K of 6, and so on. But the bottom line is every single one of those carry bits only rely on K of 0. There's no linear dependency anymore. Is that okay? Does everybody understand the general approach of how we solve the problem of relying on carry ripple? Okay? So I'm going to make a claim right now that you guys would frown at and go like, I don't think so, okay? Because I'm going to claim that K of 1 and K of 2 and K of 3 here will take the same amount of time to figure out in Logisim. So the idea is it doesn't make sense to you because obviously K of 3 is much longer. If you are the one to figure out the value of K of 3 out of the P and the G and the K0 terms, it's going to take you longer, right? And if you look at K of 1, I mean, that's so simple. It's not going to take much time. That's because from your perspective, you can only work on one operator at a time. Okay, that's just how our mind works when we are evaluating an expression. But when you look at Logisim, things can happen at the same time. How, right? So when you look at this from the Logisim perspective, we have one AND gate to deal with P2, P1, P0, K0. That's one AND gate. We have another AND gate to deal with P2, P1, G0. That's a second AND gate. And then we have another AND gate to deal with P2, G1. So we have 3 AND gates. So now answer this question. Can those 3 AND gates operate at the same time?
Yeah.
They can, right? Because they're parallel. They don't have any linear dependency between them. So that means, hey, if you give me all the P, all the G's, and K0s, those 3 AND gates can operate at exactly the same time. And they can give me the result of those individual ANDs at exactly the same time too. So that means once I have these 3 AND gates giving me the results, I can now feed G2 and the result of the 3 AND gates to a single OR gate to give me the final answer of K3. Is that making any sense? Okay, yep.
It's probably way more transistors though, right?
Yep, it does take a lot more transistors. But remember, because of Moore's law, transistors are tiny. We can actually afford to pack a lot of transistors onto the chips now. So let me try this because I figure out there's a shortcut key for me to take a screenshot. So I'm going to take a screenshot of the 3 expressions, okay? And I'm going to draw a picture. So I copy it to the clipboard. And then I want to show Zerno here so that you guys can see it. But back to my screen, I'm going to scroll down and then use, I can paste. There we go. Cool. That's what I need. And then I can now highlight and draw on this pasted thing here. All right, so let me see. It's still trying to do that. Okay, maybe enter. Nope. There we go. All right. So I'm going to give you the structure of the top. Okay. This part is a little bit hard for me because I want to point to something and then I want to work with the tablet. So I want to work out the structure of K1 first. Okay. So K1 is going to look like an OR gate, and then there's an AND gate. The output of the AND gate is one of the input of the OR gate, and then the other end, the other terminal of the OR gate just comes straight out of G0. Does that make sense? So we have G0 going straight to the OR gate, and then we have P0, K0 going to the first AND gate, and then the result of the AND gate feeds into the OR gate. So in terms of propagational delay, okay, so what is propagational delay? Propagational delay of a gate is the amount of time in order for the input, the changes of the input to affect the output. That is called propagational delay because it's not instantaneous. All right, so let me take row first, and then we'll get back to this. So let's see. Take row. There we go. And all right, so this is our row taking activity. You don't know the answer yet, so give me a second here to show you the answer. So you can, I'll put it on the whiteboard too, so that will make it easier for you guys to write down the answer. It's carry with a K. That's why it's K. Karry is the word. And then I'll give you some time to do it. I'll give you like until 11:30. I mean, that should be plenty of time to sign in if you have not signed in yet. Oh, not PM. There we go. Save and publish. You should be able to see the activity now. And for something like this simple, you can use your cell phone, you can use your tablet, or you can use the computer in front of you. And I'm gonna I will switch back to the discussion here. Those two gates are really ugly, so I'm going to redraw that. This is the AND gate, this is the OR gate. Two inputs go into the AND gate, the output of the AND gate goes into one of the input of the OR gate, and then the other input to the OR gate is just coming straight out of G of 0. Is that okay? So in order for the entire thing to finish, the first propagational delay, okay, let me pick a different color here, is going to be going from here to here. So this is going to be our first propagational delay. And then the second propagational delay is to take the output of the AND gate in order to get the correct result out of the OR gate. So it has two stages, so it has two propagational delay. So now the question? Okay. So I'll give you guys some time to absorb why there's a total of two propagational delay, because the OR gate cannot really give you the right answer until it gets the right answer from the AND gate first. And the AND gate takes a little bit of time to compute the result. Are we okay? All right. So let's take a look at K2 now. Okay, what does K2 look like from the perspective of the gate structure? So we have an OR, okay, at the end, and then one of the AND gate is going to have 3 inputs. So it's going to have 3 inputs. One is going to have 2 inputs, and then that's the entire picture. So the 3-input AND gate is going to get the inputs of K0, P0, P1. The 2-input AND gate is going to take the inputs of G0, P1, and then we have one dangling thing, which is just G1 by itself. So is it more complex? The answer is definitely. It is definitely more complex. The question is it going to take more time compared to K1? So in that case, we're going to take a look at what can be done in the first propagational delay. Those 2 AND gates can operate at exactly the same time. They give me the answer at exactly the same time. So the first chunk of time is basically for both AND gates to perform operations at exactly the same time. And then the second chunk of time is going to be the OR gate taking its input and giving me the output. So once again, we only have 2 propagational delays. Same amount of time as K1. Is that okay? All right. So now we're going to take a look at K3. So K3 is, a little bit more complex because we can see how the OR gate is going to take 4 inputs. And then we have 3 AND gates. One AND gate is going to have 4 inputs, 1, 2, 3, 4, corresponding to K0, P0, P1, and P2. We have another AND gate that's going to take 3 inputs, 1, 2, 3. Those will be corresponding to G0, P1, P2. And then we'll have the third AND gate taking only 2 inputs. That would be G1, P2. And then we have one wire kind of dangling all by itself, and that's our G2. So these all go into the OR gate, like so. And once again, it is a more complex circuit, but how much time does it take to finish the calculation in order for us to know what K3 is supposed to be? Well, it's the same amount of time. So once again, the same structure, okay? The first chunk of time is for 3 AND gates to perform all the operations at the same time. And then once the AND gates give me the answers, basically at exactly the same time, I can now compute the OR. So that's the second propagational delay. So this is the magic. This is the magic of a carry look ahead adder, because now there's no linear dependency anymore at the expense of more complex gates. But because of Moore's law, that is not too big of a deal because we can pack a lot of transistors onto the processors. So this is not a big deal. Are we good so far? Any questions? Any, comments, questions? This is actually a part of your lab. So if your lab does not contain, things that looks like this, there's something wrong with it. Alrighty. So if there are no questions, then my question is, can we generalize this? In other words, can we generalize what we have seen so far and just say, what about K of n plus 1? Can we figure out what is the structure of K of n plus 1? So the answer is yes. We can use this monstrosity to express it. So you just say, okay, I want n to be 63. Okay? And then this will generate the necessary expression to compute K of 64 in this case. So now you guys go like, but we have never seen these symbols before. Well, you're supposed to have, because you're supposed to have read ahead of me and have encountered these symbols already. Now, I personally did not read ahead of my professors when I was in college. So, I cannot blame when you guys don't do the same thing. But at the same time, I cannot expect you guys to do the same thing that I was doing in college. Because, I would say, well, I'm not going to go there, but. So what I have done is I'm going to illustrate what big OR, this is big OR, and this is big AND. So I'm going to illustrate what big AND of I equals to A to B, P of I is going to do, and what big OR, where I goes from A to B, P of I is going to do. So obviously, the first thing is, what is P of I? I don't see any P of I, in the prior discussion. Well, P of I is really what we call a predicate that depends on I. I is an index. So P of I is just a predicate. It's just a placeholder of, hey, there's this expression here that depends on I. That's all P of I is trying to represent. It's just a placeholder. All right. So the equivalent code in C or C++, by the way, I keep referring to C alone and not C++. That's because C is a subset of C++, which means if anyone claims that person knows how to use C++, that person implicitly knows how to use C already. Now, there are some minor differences where it only works in C++, but not in C, and vice versa, but it's really, really minor, okay? So I typically do not need to, go to the length of explaining, okay, this only works in C, but not in C++. Just about everything in C is gonna work in C++. Okay, so we're gonna look at this code here and say, why is it functionally the same thing as the big N notation as a mathematical symbol? So we're going to take a look at the prototype of big AND, okay? A big AND is a function. And immediately we run into a problem of what exactly is that? Yep.
So, a question, this code is not supposed to be in our notes that you,
I revised.
okay.
Yeah. So that's why earlier I said if you had downloaded or printed, you might need to do it again. Did you add your stuff to it already?
No, I just looked at the one that was on the campus site, and
That one should be updated as well,
Yeah.
unless you downloaded it or your computer might have cached it.
I have the old one also.
You have the old one?
Yeah, if I click on the module, it just pops up.
That's because it's cached. Try to refresh the page by Control-Shift-R on that page. It should refresh because it might have been cached already on your computer.
Yeah, okay.
Yep. Okay. All right.
Int star P, that's a pointer, right?
Mm-hmm. All right. So the first thing is what is this? Okay, because you are supposed to have taken what CISP310, which is all about C++, but that class does not have enough time to go through all the fun stuff you can do with C++. It just got through all the boring stuff. This is one of the fun things. This uppercase P here, with an asterisk in front of it, means it is a pointer of some kind. But the question is, what kind of a pointer is it? Is it a pointer to an integer? The answer is no. Why is it not? Because we have this thing after it. That is a list of parameters. In other words, what P is pointing to is not an integer, it is a function that returns an integer. P is a pointer to a function, which is one of the few mechanisms in which you can pass a function as a parameter to another function. Okay, so that allows me not to have to specify what exactly P is going to do depending on I. I would just leave it to some other functions to define that. The same purpose as P here as a predicate, simply as a placeholder to say, hey, there's some function P that returns a Boolean that depends on I. That's all I need to say, because I'm not here to have to specify what P of I is going to do. So that's P, and then we have the lower bound A, which is the same as this A here, and then we have the upper bound B, which is the same as B over here. So what about the code? Well, the code says we have a local variable called result, which is initialized to be true, and that's what we're going to return. Okay, we're going to return the value of result in the end. It is initialized to be true, but does it stay true the entire time? Maybe, maybe not. Okay, so we'll figure out what we're going to do with it. So we have a for loop. So as any for loop, you have the initialization. I is the indexing variable. It is initialized to A, which matches the notation over here, right? As long as I is less than or equal to B, so it is inclusive of B as the upper bound. So the upper bound B itself has to be the last iteration, and this is the post operation, which means after each iteration, I add 1 to I. So the first one is going to be A, and then A plus 1, A plus 2, A plus 3, blah, 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 B minus 1, and then finally up to B. Are we good so far in terms of what the control structure for is trying to do? Okay, so what are we going to do in the loop itself? That's the only thing we do. Result is result and, logical and, apply the function that P is pointing to with I as a parameter, which is equivalent to this thing here. So it boils down to, it is simply a huge conjunction of 1 and P of A, P of B, P of C, and all the way to P of B. It's a gigantic conjunction. That's basically what it is. The other one, guess what? It's a gigantic disjunction. Are we good so far? Maybe. So this is the generator, okay? This is the generator that, if you want to figure out, K of 128, plug in N as 127, and using this code here, you can now generate, what K of 128 is going to look like. The point is, we have a algorithm to do it. Are we okay so far? So how would this help us when everything in Logisim is hand laid out? I mean, there's no automated way to generate circuits. Well, the answer is, well, this is not going to help us in terms of Logisim. But do you think people working for Intel or AMD or NVIDIA, do you think they use Logisim as a tool to build their chips and whatnot? No. So how do you think they specify the internal or the circuitry of the processors? Something like that. And the programming language is not C or C++. They have two programming languages responsible to represent circuitry. One is called Verilog, Verilog, and then the other one is VHDL, which stands for, I cannot remember what the V stands for. HDL stands for Hardware Description Language. So if anyone here is going to Berkeley, going to the computer science program at Berkeley, that is what you need to use in the final year project at Berkeley, is to use Verilog or VHDL to specify the structure inside a processor. But by using loops like this, okay, you just need a nested loop to handle the big OR with the big AND inside of it. That's just a nested loop. Nonetheless, it is a programmatic way to generate the structure of the circuit. Are we doing okay so far with all this? Maybe? All right. So if you're not convinced that you understand all of this stuff here, we can use that generator, and it will try to generate K of 3, which we already know what it's supposed to look like, right? So shall we do that? Any objections? Okay, all right, let's do that. So I'm going to use my nifty little tool here to take a screenshot of the expression that we need. And then we stash it into the tool. Okay, so this part here is always a little confusing to me because I have to look at a different window. So we'll make one page after this, and then we'll paste it here. Control V, move it around, and now we can use a pen. Okay, so we'll say, what if n, oops, wrong color, so let me Control Z, back up. Okay, so the question is, what if n equals to 2? Okay, that's what we want to figure out. All right, so if n equals to 2, what would be the range of values for this particular I? So I equals to, what is the first value of I? 0, right? So in the first iteration, I equals to 0. In the second iteration, I equals to 1. And in the last iteration, I equals to 2, because that's exactly what I is supposed to go. Go from 0 to n, and n equals to 2. Okay, very good. So if I equals to 2, what about j? So if I equals to 0, what about j? What is the range of j? So you look into here, j is supposed to go from I plus 1 all the way up to n. So what would be the values of j?
1 to 3.
1, 2.
1, 2, 3.
Why would it be 3?
It says I plus 1, so we're just looking at I and plusing it by 1.
But n is?
2.
N is 2. So j only goes from 1 to 2. Okay? What if I equals to 1? If I equals to 1, what would be the range of j?
2.
It would be from 2 to 2, which means we have one single iteration. All right, the next one is the trick one. What if I equals to 2? If I equals to 2, j is going to start with 2 plus 1, which is a 3, and it's going to end with a value of 2. So if you go back to the control structure that we talked about earlier, would that end up with any iteration at all? We're talking about big OR here, but it has the same structure. So I is initialized to A, which in this case is 3. And in order to stay in the loop, I has to be less than or equal to B, which is 2. So do we perform even one iteration in that case?
No.
We have 0 iteration, which will give us a value of false. Okay, all right. So if I get back to this structure here, so that means in the first iteration, we're going to end up with P of 1, P of 2. So those two are ended together. How do I know those two are ended together? Because it's part of the big AND notation, right? So that means we end up with P1 and P2. And then what do we do with P1 and P2? We end it with G of I, and I is 0 at that point. So we end it with G of 0. What if J is 2? If J is 2, that means we have just P of 2. And then we end it with G of I. I is 1 in this case. So we have G of 1 and P of 2. And if I equals to 2, we do not have anything generated from within here except for true, because that's the default value that we're going to return. But I equals to 2 in this case. So we have G of 2 and true, which is just G of 2. Are we doing okay so far? So G of 0 and P of 1 and P of 2, G of 1 and P of 2, G of 2, those terms are generated to be ORed together because of the big OR notation. So now we have to say, okay, fine, yeah, we're going to OR these items. Okay. So that takes care of, okay, so this is going to take care of taking care of this portion of the expression. So now we have the other expression to deal with. That one is significantly easier because in that case we just have a big and I goes from 0 to n. So once again, we are going to look at, okay, so I equals to 0, I equals to 1, I equals to 2. When I equals to 0, we just crank out P of 0. When I equals to 1, we just crank out P of 1, and then we have P of 2. And then those have to be ANDed together. So we have P of 0 and P of 1 and P of 2. And then we have this extra K of 0. So that also has to be ANDed with these 3. So now we have K of 0, P of 1. Oops, did I make a mistake? Nope. P of 0, P of 1, P of 2. That is taking care of this portion here. Are we good so far? How the generator works? So in the end, what do we get, right? So in the end, we just have all of this stuff here. This is a big OR. And then we just have to say, oh, this whole thing or this. Why? Because we have this little OR in between. So now we have one gigantic OR that. That becomes the final result. So the question is that actually what we ended up with? So let's double check that. Okay, so we're going to go back to the notes. And then I'm going to copy and paste the K of 3 because it's not easy to see it. So I'm just going to do the same trick here. This is K of 3, and then we'll double check. Okay, so copy the clipboard and then paste it. Oh, that's not what I wanted. Paste. There we go. You cannot see it yet. I just have to move it a little bit before you guys can see it. There we go. And then I can show you what I'm seeing. Okay. So the question is, are we getting back the same K3 that we had earlier? So let's double check. G2 by itself in the big OR. Yep. G2 by itself in the big OR. G1P2. Oh, we don't have a G1, P2, but we have a P2, G1. Would that be okay? It's going to be okay because conjunction is commutative. Okay, you can swap the order between the left and the right operands. It doesn't change the result. Okay, so that's why G1, P2 is the same thing as P2, G1, just like multiplication. What about G0, P1, P2? We don't have that, but we do have a P2, P1, G0. All right, same thing, okay? Because conjunction, like multiplication, is commutative. We got one extra thing here, which is K0, P0, P1, P2. We got K, P2, P1, P0, K0, just everything being backwards, but it's the same thing. So we got exactly the same thing. So the generator does work, at least for K of 3. Yep.
You just generated all of this off the end, just plugging into the formula.
Yep.
Okay.
Yep. Because I want to verify, because I want to double check to make sure that the generator is consistent with the algebraic version of deriving K3. Yep. So, are there any questions? So without any questions, I do want to give you a kind of a map of the forest, because a lot of this stuff here is like pine needles, okay? And when you spend all day looking and picking up pine needles, sometimes you lose track of where you are in the forest. So we're going to take a step back and take a look at the forest, because I want to show you, the context of what we have talked about so far, because I think that is important. All right. So the first thing we talked about is the 2P2N circuit using transistors, and we ended up building a NAND 2 gate, right? So we basically used 4 transistors to make a NAND 2 gate. From the NAND 2 gate, NAND 2, because the 2 refers to the number of inputs, so there are 2 inputs to the NAND gate. So from that, we say, hey, we know how to do a NOT gate, we know how to do a logical AND, and then we also know how to do an OR gate out of the NAND gate. So NAND is the universal operator because it can emulate the other 3. So after that, we took a pause, okay? We stopped working with the logic gates. Instead, we worked on bases, right? We got value on one side. This is a value, okay? How many fingers am I holding up? That is a value. The moment you call that 5, it's a number, okay? 5 is a base 10 number to refer to the quantity that you are seeing here. But you can also refer to this as 101 in base 2, because it is 4 plus 1. So we differentiate what is a value versus what is a number. A number is a representation of a value, and that can be basically an infinite number of ways to represent the same value. So we talked about base, conversion, and value. So basically you can go in one direction, but you can also go in the opposite direction. If I give you a number, you can figure out what value it is representing. If I give you a value, you can also convert it back into a number given whatever base that I want you to work with. So we talked about that. And the importance of that discussion is, so that means everything that we can represent in base 10 can also be represented in base 2, because everything inside the computer is in base 2. Because the only thing we can observe, or the only thing we can tell, is whether the voltage of a particular point is above a certain threshold, meaning it is a 1, or it is under a certain threshold, which means it is a 0. So we need to be able to say, okay, the computer can only work with base 2, but can we represent everything, all the values that we know of in base 2? And the answer is, yep, we know how to do that. And then after that, we talk about binary addition. Well, actually, I should say just addition by itself. So when we talk about addition, we are only talking about multi-digit addition, which is something that you already know how to do. So it's multi-digit addition. So that has to do with the structure of how you compute the carry, how you compute the single-digit sum, and how you put everything together. That defines the structure of multi-digit addition. So out of that discussion, we term, x and y, those are the two numbers that we are adding together. We have an extra row that we call q, which is kind of intermediate. We have one row called k, which are the carries. And then we have the final result, which is the sum. So these 5 are the rows of a multi-digit addition structure. And then we look at those 5 rows and we ask the question, I ask the question of, but how do we figure out those numbers? How do we figure out the digits? So we define, so we end up with an R function, right? Which is the single digit sum. We also end up with a C function, which is to determine whether there is a carry when we add A and B. So A and B in these two cases represent single digits of a particular base. Is that okay? So we have a general equation or the general function of how to compute R and how to compute C, and that's going to work regardless of the base, even though the example are only for base 10. But as you pointed out multiple times today, just change the 10 to a 2, and now we can work with base 2. But base 2 comes with its own advantages, because in base 2, just earlier today, we figure out that R of AB is really the same thing as A exclusive OR with B. That's the symbol representing exclusive OR. And then C of AB is really just A and B. So we figure that out, and then we sort of go like, oh, this is great, because now we can use logic gates to compute R and C. Cool. And then we also figure out what is Q of I, right? We figure out that Q of I is just R of Xi, Yi. This is all from the earlier part of today's lecture. I'm just putting it in here. And then S of I is R of Qi, Ki. And the most complicated one is K of I plus 1, which is C of Xi, Yi, or C of Qi, Ki. So we talked about this, but since your R is now a Boolean expression, C is also a Boolean expression, and this is actually an OR, so now we can compute Q, S, and K using just logic gates. All of that was from last week. That's how we ended up with the carry ripple adder. What we did today was to do the trick of saying, hey, can we make K of I plus 1 not to depend on K of I? And we figure out the trick to do that is to define G of I, P of I, and then do some algebra stuff, right? So that K of I plus 1 can now depend on just K0 and all the P terms and all the G terms. And the P of I is defined to be Xi or Yi, and then G of I is defined to be Xi and Yi. So that's a really kind of short recap of what we have talked about so far, which is basically 2 weeks and a half. Do we have any questions about that quick recap? It's just like anime series. Sometimes the author have no time to actually draw anything new, and they decide, okay, we're gonna just take all the clips from before, kind of string them together to retell the story in a very short way, and that's gonna use up the time of one episode, and I can take a break. But that's basically what this is, okay? I just recapped what we have learned so far, but in the context. So the biggest thing that we have right now is we now know how to perform addition in base 2 in a quick way. And everything can translate to transistors. So that is where we stand right now at this point. Okay, you guys do not seem very excited, but this is actually supposed to be an exciting moment because, I mean, isn't that great that we can actually do all this stuff here using just transistors? We can now add and figure out the sum of 2 values using just transistors. Woohoo! Yes. All right, so what we'll do now is I'm going to release the lab. So you guys can, if you want to take a short break, that's fine with me. I'm going to give you guys up to 1:20 to get the lab done. So once again, this lab may be a little bit more involved, so I would definitely try to make sure that you get enough time And there's an access key. So let me show you the access key first. So the access key is 3x3 part 1. Which has nothing to do with the manga. There's a manga called 3x3 or 3x3. So it's due today at 1:20 p.m. And there's a companion activity. Let me just kind of show you what I mean by that. So the first one is this is basically a quiz, but it will guide you through the process of making the circuits of K1, K2, and K3. Now, when you do make those circuits, there are a few things that are important. First of all, the components are case sensitive. So if the assignment, if the instruction says if K1, K2, K3 of lowercase k, use lowercase case, okay? And then the second thing is the location of the pins are also important, okay? So make sure that in your appearance of the circuit that the locations of the pins are correct as well. So don't move things around, okay? Positions are important. After you're done with the circuit, this is how you submit the actual circuit. So you do have a circuit file to submit at the end of today's lab. So those are the two components of what you need to do for the lab time. You can get started now. I mean, they're all released now. Or you can take a short break, whatever you guys want to do. So I'm going to